Hello again. We continue chapter 7 with 7.7. We are looking into how to approximate a definite integral or an area under a graph. Why will I do that? Why would I even need that? It's because, let's say, from 0 to 1, from the integral from 0 to 1 from cosine x squared dx, we cannot find the antiderivative. So we can evaluate it from 0 to 1. A computer algebra system, a calculator, a software can, but we cannot. So we can still approximate this. And we saw in chapters 5, we looked at a few methods using the leftmost point, the rightmost point, and we also look at the midpoint rule. Okay, in chapter 7 right now, we're going to look again at the midpoint rule and two other rules. So number 1 will be, again, midpoint rule. Number 2, the trapezoidal rule. And number 3, Simpson's rule. Simpson's rule. From these two, midpoint is better, has less error. Midpoint is better. From these three, Simpson is better. Has a better approximation and less error. Okay, so let's start by looking at the midpoint rule. I'm going to just refresh your memory on a very simple situation. Let's say we have a function between a and b, and let's say we are dividing this interval into two pieces, two subintervals. So this is our f of x, n equals 2 subintervals. The midpoint for this subinterval would be this. The midpoint will be this. I'm going to call it x1 and x2. And of course, where it hits the graph of the function, I will draw a horizontal line. And this is the area in question. And again here, and here's the area in question. So basically the integral from a to b from f of x dx will be approximately this distance is delta x. Of course, this one is also delta x. And delta x is denoted by or determined by b minus a divided by the number of subintervals. In this case, it's 2. I'm going to write the general formula. So then for the midpoint rule, we have delta x in front, and we have f of x1 for this simple example. F of x1 plus f of x2 multiplied by delta x. Now, we can also estimate, we should say, determine an upper bound, a maximum for the error. So the max error for midpoint rule in absolute value, because it could be negative or positive. So E midpoint rule is less than or equal to k, b minus a, we know what they are, to the third power, divided by 24 n squared. We know what n is, the number of subintervals. We know what b minus a. The question is, what is this? What is this constant, k? Well, this constant k comes from the following inequality. The second derivative in absolute value less than or equal to a number k on, of course, the interval a comma b. And we'll see how we will determine that k in a minute. So this is our problem. We want to determine the integral from 0 to 1 of cosine x squared dx. We know we cannot determine this exactly without a calculator or computer or software or so on and so forth. So we are going to approximate it with 4 subintervals using the midpoint rule. So we have, again, and we're going to go through the same problem, the same process for all methods, all 3 methods. Okay, so we have 0 to 1 from cosine x squared dx. We cannot find the antiderivative. We cannot determine this exactly. Good. So the interval 0 to 1, so n equals 4 subintervals, and a comma b in our case is 0 comma 1. So we're going to look at the interval 0 to 1, divide up into 4 subintervals, with delta x being 1 minus 0 divided by the number of subintervals. So this is 1/4, which means this is the 1/4, meaning this point here is 0.25, this one is 0.5, this one is 0.75, and this one is 1. In order to determine a midpoint, I know that 0.25 divided by 2, because that's half right here in the midpoint. Let me use a different color here. So this will be, this point here is 0.125. This point here is 3 times 1, 2, 3, 3 times 0.125. This point here is 5 times 0.125. And of course, this one is 7 times 0.125. So then the integral from 0 to 1 from cosine x squared dx will be approximately delta x, which is 1/4, f of 0.125 plus f of 3 times 0.125. I don't care to calculate. You can, of course. F times of f of 5.125 plus f of 7 times 0.125, and close the bracket. I do have a video on this method posted already. Before you continue, you should look at that. I will definitely show it. Where is my calculator? I will show it here. So in y equals I, for this method, I don't need anything, so that's fine. So we go to stats, and we want to edit. I'm going to clear list L1, highlight the top, clear, highlight the top, clear, and enter. And I will enter 0.125, that's my first midpoint, 3 times 0.125, 5 times 0.125, and the last one, 7 times 0.125. So I have the midpoints already entered in the X list, or list L1. For list L2, I will enter the function, meaning 0.25, and then multiplied by, careful, I should have checked. I know my calculator is in radian mode, but for any trig function, please make sure that you go to mode first. I'll show it in a minute. Let me finish entering list L2, and we will check and make sure that the mode is in radian mode. While list L2 is highlighted, and again, I have a video posted on this already. L2 is highlighted. We have cosine, but now what I want to enter is list L1, and that has to be squared, and then close the parenthesis. And when I hit enter, all 4 numbers will pop up. 0.25 times this, and then the next line 0.25 times this, and then so on and so forth. So I press enter, and I have all of them. Again, so let's check. Go to mode, radian mode, not degree mode. And then I go to stats, and I want to perform calculations with stats. And what I want at this point is to press enter here. Make sure that you have list L2 because we want to add up only list L2. And here's the sum. And I copy all of them because then I'll decide how many digits depending on the problem, the requirement. So 0.9089067907. So it depends on what the problem is asking, maybe 2 decimal digits, maybe 4, who knows. I copied the whole thing. So this is the approximate area. Can the calculator calculate this very, very well? Yes, it can. Again, I show that in another video. Go to math and press 9, and this is 0 to 1. And we have cosine, and that cosine is on x squared. Close another parenthesis, and then dx, and press enter. So extremely close. So I'm going to put here in parentheses with TI 84, I got 0.9045242379. Just to show you that we really don't, we're not going to do anything with it. I'm just going to show that the fact that basically the midpoint rule is it's a better approximation than what we're going to obtain with the trapezoidal rule. Before we continue, we want to determine the maximum error, the upper bound of the error. So we're going to perform this calculation. And then also, we're going to answer another question on the same method in a minute. So now we have the approximation with 4 subintervals with the midpoint rule. And at this point, we want to determine so I'm on page 3, the absolute value, which is less than or equal to k, b minus a to the third, divided by 24n squared. We already know that this is 2 minus 1, which is 1. 1 cubed is 1. We already know that the denominator is 24 multiplied by 4 squared. We had 4 subintervals, so this is 16. Let's see how we determine this k. So first, the function is f of x equals cosine x squared. And we need to determine the second derivative, put it in absolute value, and say, oh, I think I can show that the absolute value of this is less than or equal to whatever number we come up with. We'll see in a moment. So first of all, we have work to do in order to determine the second derivative. Okay, so let's find first the first derivative. So cosine prime is negative sine x squared times the inner function prime, which is 2x. So we have negative 2x and sine x squared. And this is just the first derivative. We need the second derivative. Careful now, because now we are using the product rule. We can leave negative 2 outside. The first function prime is 1 times the second function plus the first function times the second function prime. When I differentiate sine, I get cosine of x squared times the inner function prime, which is 2x. Let's try and simplify this a little bit. So we have negative 2 sine x squared, and this is 2x times x, 2x squared times negative 2 minus 4x squared cosine x squared. So now let's think. Always remember the interval in this case is 0, 1. 0 radians, 1 radian. Well, 1 radian, as we know, is approximately 57 degrees. So you can think in terms of 60 degrees. Okay, so let's take a look. So the second derivative. Now, we should look at this function, put it in the graphing calculator, and see if it's an increasing function or a decreasing function. That is important. Now, what happens at 0? So the second derivative at 0. This is 0, and this is 0. This is not 0, but there is a 0 in front. Let's see the second derivative at 1, I meant to write. Okay, at 1, or 1 radian, or 57 degrees, roughly 60. So here, sine of 1 is a sine of 60 degrees, which is the square root of 3 over 2, with a minus 2 in front. So that would be negative the square root of 3. Now here, with 1, so this is negative 4. And cosine of roughly 60 degrees is 1/2. So times 1/2. So this will be negative the square root of 3 minus 2. Okay, so this I could say, but first I have to look and make sure that this is an increasing function or decreasing function. It doesn't matter, but I need to know which one. So obviously this is the 0 and this is the negative. So it appears that the function is decreasing, but I need the absolute value, right? So I would say that this must be less than or equal to the square root of 3 plus 2. So in this event, this is my k. That needs to be put in the graphing, in the relationship. So I like to double check, and I'm going to enter in y equals negative 2, and then sine of x squared, and then minus 4x squared, and then cosine of x squared, and close. Of course, all I need is the interval 0, 1. So 0, 1, and I don't know, negative 5 to positive 5 with a scale of 1. So 0, 1 with a scale of 1, and negative 5, 5 with a scale of 1. And I press graph. Good. Okay, it kind of appears to be turning up a little bit here. We can zoom in. So I would recommend that I can determine the minimum here and see what happens with second and calc. And I want the minimum. And I'm going to say between, why don't I just extend the interval? I'm going to extend the interval a little bit so I can put the 2 in there. Put the 1 in there, actually. Ah, good. So I want the minimum with second and calc. I want minimum, which is 3, and I want the minimum between 0 and 1. That's all I care about. Okay, so the minimum is at roughly 1. Okay, so this is just an upper bound, right? So this number is 3.84 in absolute value, of course. And we can do that, right? So we can change square root of 3 and plus 2. Okay, so we get 3.73, and the other one between 0 and 1, it was 3.84. Okay, so the arrow bound, the upper bound, 3.84 divided by 24 times 16, and we get 3.84 divided by, don't forget 24, and divided again by 16, or you put parentheses in the denominator. So 0.01. Now I would like to answer another potential question here. What is the potential question here? The potential question here is, what if I want to make sure that the error is less than 0.0001? Find n, the number of subintervals, to guarantee that. Okay, so in that case, for this particular situation, of course, we are still talking about 0, 1, And we determined the 3.84. So I have 3.84 divided by 24 multiplied by n squared, and that is less than or equal to 0.0001. Okay, if that's the case, I will be cross multiply, and then I have, I will divide by 24, so n squared greater than or equal to 3.84 divided by 24 times 0.0001. And then take the square root from this number. So let's see what we get. So 3.84 divided by, I'll put parentheses in this case. I didn't even need to multiply that with the calculator, but anyway. And then I take the square root from this, from the previous answer. So I got 39.79, so then n must be 40 or more. So 40 subintervals. To guarantee that the error in calculating or estimating this integral using the midpoint between 0 and 1 has an error of less than 0.0001. It needs 40 subintervals. Okay, enough with this method. Moving on to the next one.